Washington State University. Go Cougs!
Hello everyone. In this video, we're going to cover Lesson 6 of the Activity Change Detection module. In the previous lesson, we discussed physical activity change detection and how a change score function f is needed that accepts two windows of data and returns a numeric value representing the change between these two windows. I mentioned that there are several options for algorithms we can use for this change score function f. One great algorithm is called the virtual classifier, and in this lesson and the next lesson, we're going to discuss the virtual classifier approach and implement it in Python. So let's begin. The virtual classifier is part of a change analysis technique that was proposed by Hito and colleagues in 2008. It utilizes a virtual binary classifier to detect and investigate change between two sets of data. Before we discuss the details of the VC approach, I'd like to mention that there is some background that I'm going to assume that you know. The background I'm going to assume that you know is binary classification, evaluating a binary classifier using its accuracy, and also k-fold cross-validation. Now, if you're familiar with these topics, that's great. Go ahead and follow along with me. If not, please take time to pause the video now and read the background information I've included here. If you'd like to know more about any of the background information, I have included links from popular sites like Wikipedia where I've taken this information. So here's the binary classification background information. Here's the classifier performance background, including discussing accuracy, and also k-fold cross-validation, with a really great graphic here for explaining the different folds in cross-validation. Now let's discuss the steps in the virtual classifier approach. First, we assume the virtual classifier approach is being used for PACD for large window sizes. So I would say at least 5 to 6 days of data per window. The first step is to extract a feature as a feature extraction step where two windows are reduced into sets of n daily feature vectors, where n is the number of days in a window. Each daily feature vector of f sub I, corresponding to window sub I, is labeled with a positive class. Each daily feature vector of f sub I, corresponding to window w sub j, is labeled with a negative class. Step 3, the virtual classifier trains a decision tree model to learn the boundary between the virtual positive and negative classes. The resulting average prediction accuracy from k-fold cross-validation is represented as P sub VC. If a significant change exists between the two windows, P sub VC should be significantly higher than the accuracy we would expect from random noise. Let's call this random noise accuracy P sub ran. For two equal size windows, we can expect P sub ran to be 0.5. For the significance test, a critical value is determined, called P sub critical, from the inverse survival function of a binomial distribution. Binomial because we're using a binary classification, at which n Bernoulli trials are expected to exceed 0.5 at alpha significance. If P sub VC is greater than or equal to P sub critical, then we can say with alpha confidence that a significant change exists between the two windows, W sub I and W sub j. In the next lesson, we'll discuss this in more detail and implement code to compute P critical. Now let's take a look at implementing steps 1 in this lesson and steps 2, 3, and 4 in the next lesson with our example data from our Fitbit steps. So we'll return to our data set where we have 21 days of steps data minute by minute. Since there are 21 days of data, we have options for how we want to window our data. Let's window it into 3 one-week windows. That way we have at least 7 feature vectors for each one of our virtual positive and virtual negative classes. So our 3 one-week windows are W sub 1 starting at day 1, W sub 8 starting at day 8, and W sub 15 starting at day 15. Now, we can perform either a set of 2 baseline or 2 sliding window comparisons. For baseline comparisons, we can compare our reference window, week 1, to week 8, which is our second week. And again, we can compare week 1, but this time to week 15, which is our third week. For sliding comparisons, we can compare week 1 to week 8, so our first week to our second week. And then a second comparison can be our week 8 to week 15, which is second week to our third week. For simplicity, in this example, we're only going to perform a single comparison of week 1 to week 8. That will cover number 1 in both baseline and sliding comparisons. So let's first go ahead and load up our 21-day example data frame. Here's my code to load it up and set a date time index for the index. We'll see the first 5 rows of the data frame corresponding to the first 5 minutes after midnight, and our columns here are 21 days. Now we're ready to begin the virtual classifier approach. First, we need to perform our feature extraction step. So we're going to compute features that are likely to be indicative of changes from day to day and from window to window. And remember, our window size is 7 days, so changes perhaps from week to week. For this example, our window size, n, is 7 days. So we're going to extract daily features, and I've included 8 simple ones here that are easy to compute, and they can be useful for detecting changes between days and between weeks. So the first 4 are fairly straightforward to compute: total steps, max steps, average steps, and standard deviation of steps per day. So let's code those up because we can do them quite quickly. So let's write a function called computeFeaturesDF that's going to accept a data frame. So first thing we're going to do is create our features data frame, which is going to be a data frame with the index set to the columns of our data frame df. That's our steps data frame. So our columns in our steps data frame are dates. So dates are now going to be our index, and our columns will be our features. So let's do our first one, features df sub total is going to be assigned df.sum. So this will sum down each column. Features df sub max is simply df.max. So this will take the max of each column, which will be essentially the maximum number of steps taken per minute for each day. Next, let's do mean and then standard deviation. So this is the average number of steps taken per minute for each day. And of course, the standard deviation associated with that mean. Return the features data frame. And let's call this function and print out our features data frame so far. It will be a 21 by 4 data frame. So here are our dates as our index, 21 of them, and we've added 4 features so far. So what this means is, for example, on October 1st, 2015, 5,097 steps were taken in total. The maximum number of steps taken per minute was 118 steps per minute. The average number of steps taken per minute was 3.54, and the standard deviation is 12.6. Now let's take a look at the last 4 features that I want to add. We're going to add physical activity intensity percentages for 4 different intensity levels. So we're going to add a feature called sedentary percent. That is going to represent the percentage of the day that less than 5 steps per minute were taken. And we'll repeat for low, which is greater than or equal to 5 but less than 40 steps per minute. Moderate, greater than or equal to 40 steps per minute but less than 100. And high, greater than or equal to 100 steps per minute. We're going to make use of a function from pandas called cut, which is going to bin our data according to our specified cutoff values here, 5, 40, and 100. So let's take a look at the documentation for pandas cut. So pandas cut is going to accept 2 arguments. The input data to be binned, it has to be one-dimensional. Bins, which is going to be a sequence of scalars in our case to define the number of, to define the bin edges, allowing for non-uniform bin width. And then labels used to label the resulting bins. So let's go ahead and add labels for our intensities. These are going to be our column names. So we'll have sedentary, low, moderate, and high. Now let's go through each intensity and stub out a column in our features data frame for the intensity. So for intensity in intensities, we'll do features df sub intensity. So adding a new column called intensity, and let's just broadcast missing values. So what we've done is stub out these columns, sedentary, low, and moderate. Now we're ready to set up our bins list, which is what we're going to pass into our call to the cut function, along with our daily step counts. So let's go ahead and declare an empty list called bins. Now, how we're going to fill bins is we're going to have to specify values that are going to be used to discretize our data or chop it into categories or bins such that our values are exclusive of left and inclusive of right. So, for example, for sedentary, our interval for our bin is going to be -1 because it's exclusive, so that'll give us 0 inclusive, and inclusive of right, which would be 4. For low, this is going to be exclusive of 4 and inclusive of 39. For moderate, this is going to be exclusive of 39 and inclusive of 99. And for high, this is going to be exclusive of 99 and inclusive of our max value. So we first need to compute this max value. So the maximum value is going to be the maximum number of steps taken per minute in the entire data frame. So this will be our features df submax dot max, or we could simply do df dot max dot max. Now let's set up our bins to be -1 to 4, 4 to 39, 39 to 99, and 99 to max val. Now finally, we're ready to start adding in our values. So we're going to do this one at a time. So for each date in df.columns, we're going to call pd.cut, which is going to return a series. For each index in this series, it will have a label according to what intensity value this minute corresponds to. So intensity ser, this will be pd.cut, passing in df sub date. So there's our one-dimensional series for step counts for this day. our bins, and labels for our bins called intensities. Now let's print out intensities there so we can see what it looks like. Okay, so each minute has been labeled as sedentary, low, moderate, or high. So we can see here that the first 5 minutes are labeled as sedentary, but the 6th minute is labeled as low. Okay, great. So now let's go ahead and get the counts for each category. Intensity, level. And let's print out counts so we can see what it looks like. So for each day, we have a series for long, sedentary, 1,245 minutes of the day, low, 158 minutes a day, moderate, 32 minutes of the day, and high, 5 minutes of the day. So now we just need to go through each one of these intensities, convert those minutes into percentages, and add it to our features data frame. So for intensity in intensities, our percentage is going to be counts sub intensity divided by the length of the data frame index times 100. And now we'll add to features df at date at intensity this percentage. Now we are ready to run this code, and here we see all of our percentages for sedentary, low, moderate, and high. So the last thing we're going to do is save this for the next lesson. So here's the file name that I'm going to use, just adding a features_df.csv onto the end of our base name, and let's write our features_df.tocsv. And this is where we will pick up in the next lesson.